All right. So, good afternoon, respected GEC members, dear faculty, and the participants. Welcome to my thesis defense with research topic islanding detection for inverter-based distributed generation using unsupervised learning. So, these are some credentials and affiliations and sponsors. For the research problem, islanding detection for inverter-based distributed generation using unsupervised learning can be disintegrated into three keywords, which includes islanding detection, which is a traditional power system protection, which is also called as loss of main protection. So, a well-established literature is already present in islanding detection problem, and the second keyword is inverter based distribution, so which means that I'm specifically applying islanding detection problem for specific systems, which includes inverter based distributed generation, and we will see why I'm doing specifically or particularly for inverter based distributed generation, which is actually a topological advancement in electrical power systems. The third keyword from the title is unsupervised learning. So the methodology of action to uh, detect islanding in the indicated topological power system is unsupervised learning, which is a model and data centric intelligence approach. So specifically in unsupervised learning, we have used deep learning as a methodology to detect islanding for inverter-based distributed systems. Following are the keywords which I have been using for my research and publication. The key features of my research work is based on three particular models, which in which one of the most prominent is IEEE standard 1547 standard model. The second second model is a multi-inverter system, which is also based on 154 system model, but it has multiple inverter systems incorporated with the adjacent buses. And the last system is 13 bus system to to check the effectiveness of the system over unbalanced system and complicated systems. So the methodology I have applied here is active frequency drift, which is implemented in the inverter control, and an AI-based algorithm is implemented also on the active frequency drift. And an automated script of algorithm was established during the literature during my research, which includes the data generation, data cleaning, and active detection of for the problem. A rigorous simulation was carried out for all the possible power mismatch cases in order to justify the statistical significance of the work, and an offline and online validation theorem design was presented in my research. This was a noble contribution of the work in such a way that in the existing literature, no online and offline literature validation scheme has been yet presented as far as my knowledge. Finally, the work is concluded by demonstrating the statistical significance of the AI code along with the active frequency drift in perspective of few parameters, including F1 score, dependability index, and security index, which we'll be discussing in detail in the later slides. So this is the agenda for the thesis presentation, which includes the motivation for the research, what is actually the research problem, how a hierarchical layered approach is implemented to resolve islanding detection problem, the results, and the specification of modeling and simulation presented there, a technical comparison of of the proposed scheme with the existing literature, and following with its novelty and challenges in the way of implementation, then finally leading to conclusion and the future aspects of the work. So let's start with research motivation. What was my research motivation? In 2017, I was observing a lot of cascaded blackouts and brownout events in the electrical power systems. From, if you see in the newspapers, from 2015, then 2018, and in fact leading to 2020 in January 10, There have been cascaded power outages in the systems, and yet the system credibility is still questionable in perspective of protection failure or low reliability. Plus, we are moving towards a generation of electricity where we are about to implement the renewable energy. We are integrating renewable energy resources with our systems. So it was a greater question to answer that are we still if we are not capable enough to comply the requirements of an existing framework of electrical power system, how are we going to be capable to address the issues by a complicated system which is about to be implemented in the coming future? So this inspired me to further investigate the issues. So I just had a understanding of the traditional power system, which is actually the industrial age power systems, or which was introduced in age of industrialization, in which the main grid systems feed the residential and industrial loads by means of a simple and sophisticated control and protection scheme. And then we are now moving from age of industrialization to age of information, and the traditional power system are being replaced to distributed power generation systems. In these traditional distributed power generation systems, more and more renewable energy resources are being integrated on the load and sides, which means a decentralized way of implementation of electrical power system where energy resources are scattered all over the network, and that introduce a very catastrophic problem in the situation, which is that the power flows from the grid side to the residential side are not unidirectional now. So there can be power flows from main grid to residential sites apart. There can be power flows from a residential and industrial side in the form of microgrids and in the form of distributed energy resources towards the main grid. So it's a bidirectional system which increases the complexity of the system, which almost makes all of the electrical protection less reliable and questionable. So in this whole situation, we proposed there is an immense need for a sophisticated control and protection schemes, and for this we have to modify all of the existing framework and all of the existing structure of the system, which is impossible at this end because all of the equipments and the sophisticated control system is quite costly. So my approach to solve this question was the problem was to, despite of replacing the whole infrastructure, if we add an intelligent systems at the local servers, we can achieve a optimal solution with the lowest cost. So this inspired me to work on intelligent control and protection systems, and then I specifically picked up an area in intelligent control and protection systems by inspired by a renewable energy report 2020 published by IEEE, which indicates that 23 of the world's world electricity population is to be further added um, as renewable energy resources. That is like 23%. It's a huge amount of renewable energies about to be incorporated with the existing world's electrical power systems. Also, we had news in April 23, which indicates that Pakistan will shift to 60% of clean energy by 2030. So we have to be very careful what's coming next, especially when we have so much sensitivity to blackouts and brownouts. So this inspired me to work on islanding detection problems, um, uh, which includes that if a lot of distributed energy resources are incorporated in the system, this increases the system inertia, reduce the power quality of the system, and parallel operation comes as a catastrophe. Grid penetration issues are prominent, and high droop gain characteristics for DERs, which we'll be discussing in the later slides. So the point is that we want a very sophisticated control protection scheme, and the first thing that we can do to address the blackouts and brownouts for the system is to propose a sophisticated control and protection scheme for islanding detection. So what is an islanding detection? That when a part of a system is compromised by any means, maybe overloading or any fault situation or any hazardous situation, the system disintegrates itself into small islands, which works independently with its local distributed energy resources serving itself. And when the system is has acquired a healthy situation and has addressed the threat which was integrated there, the system which is distributed into island is collected together and integrated together to form the network again. So this technique is called islanding, and a lot of literature has been published on this. And but for inverter-based distributed generation, there is a limited uh, literature there, and we have proposed a scheme for that. So let's just start with the islanding detection problem. So this was basically the IEEE standard 1547 islanding model, in which consists of three parts, which is the main grid, which is attached with a local load and a distributed energy resource. And when the grid is lost, which is simulated by here with the utility breaker, when the utility breaker is opened, the grid is lost and the distributed energy resource and local load are operated independently, energized by themselves. So according to the standard, the islanding should be detected within 2 seconds after the occurrence of the event. So this is the standard detection of islanding within 2 seconds. Then after that, what's the decision it is about to take, that either they will continue to operate as an island or the DER has to be is to be shut down. That depends on the control topology of the DER itself. So classification of islanding events is distributed in various aspects. Let's say in the form of duration, it's a short-term and long-term islanding events, which is classified in the existing literature. Then they have another nomenclature for islanding detection, which is nature of causality, that is intentional, unintentional. Then the nature of the network, which is the topology, is schedule and unscheduled, and operational philosophy, which is remote and local. So the main literature is surrounded by the local techniques of islanding detection, which includes active, passive, and hybrid methods of islanding. So in methods are more likely to be more prone to power quality concerns, because an active controlled perturbation is introduced in the inverter control system. So a continuous signal is injected to the inverter current that leads to power quality deterioration. But at the same time, active methods are quite effective in detection, especially for non-detection zone, which will be uh, uh, explaining in the later slides. However, passive methods do not change the original signal itself, and thoroughly works to improvise and improve the sensing techniques. But they are based on analytical framework and mathematical framework, which usually is about to fail if there are a lot of distributed energy resources with high droop gains in the system. So mathematical and analytical framework would eventually fall. A combination of both, a small perturbation with improved sensing, is implemented in hybrid system, and our proposal is a hybrid intelligence approach as well. Then hierarchical layered approach. So we proposed here a hierarchical layered approach, which consists of three layers in the island for islanding detection. The first layer is an active layer, which is actually an abstract from the active literature of the islanding detection part, namely called as active frequency drift. So an active frequency drift algorithm is hardware control is implemented in the inverters, and leading by another layer, which is an intelligent detection autoencoders, which are implemented over active frequency drift. As an intelligent algorithm continuously watchdogging over the parameters hyper tuned by active frequency drift, and it's continuously watchdogging the effects of those values. Once the intelligent detection layer is implemented, an online validation with a secondary multi-feature analysis parameter is added, to create an effectiveness and to improve the reliability of the system with active and online validation of the systems. The first layer is active frequency drift. A pseudocode is presented on the right hand side of this of the slide. The topmost part is an active frequency drift component, which is implemented to the electrical power system, represented by the mathematical equation at the left, very left and top. So this is the equation which was implemented on the inverter control by various control techniques, and as a result, as you can see, a frequency drift or a perturbation is introduced in the electrical wave.
Point over there. Okay.
All right. So as discussed, this was the mathematical framework, and this was the result of active perturbation as a result of implementing this mathematical framework to the classical layer. Then an intelligent detection layer was implemented in the autoencoder part, which consists of two parts, which is a generative network and degenerative network. In an analogous way to explain this intelligent algorithm, we can say that detection and generative methods, generator networks are two AI codes which are competing with each other. One is trying to generate a signal that another cannot detect, and the detection network is trying to its very best hard to detect the signal. So in this way, both of the AI codes are competing with each other to train the signal. So this is the basic analogy which is explained in this mathematical structure, which eventually we can discuss in the question and answer section. So in this section, so in this way, the autoencoders are trained and are able to detect islanding. The process flow diagram for the universal code or the single click code was implemented that on single click, the universal code was capable of initializing the model, run the model, then a feature selection, feature extraction were carried out from that on which feature we have to study islanding. Then the data cleaning for that extracted feature was done and autoencoder was trained over that parameter. Detection stride was done and then the islanding detection time was indicated. Offline validation schemes were also presented, includes fault right through cases, load variation cases, parallel operation cases, unbalanced system cases to ensure the statistical significance of the work. Apart from these, the third layer, the intelligent online validation cores, is another intelligent layer also based on autoencoder itself, and it's working in parallel. You can, if you can see on the pseudocode side, so both of the online validation and detection intelligent algorithm are working simultaneously to combine themselves in the form of control logic that initiates the trip to the power systems. Then modeling and simulation. As already discussed, that I have been using three models for islanding detection, that is 1547 standard model, an extended parallel grid feeding inverter model, and an unbalanced 13 bus system, and along with the universal code which was demonstrated in the previous slide. So after a rigorous calculation, following parameters were calculated and the rigorous calculations and islanding detection was carried out for this, and 3 out of 6 best parameters were selected for islanding detection. The rate of change of frequency was considered as the primary detection parameter, and the rest of the two, phase angle pulse width, voltage and current, were considered to be a secondary feature for islanding detection in the online validation layer. So this is the implementation of active frequency drift. A minimal amount of differential frequency component was injected into the system, which can be represented in the waveform. A small drift is created. So whenever there is a drift, when an islanding is initiated, the values of the frequency are drastically raised. So for these values, the autoencoder was trained for the parameters which are mentioned here, the data point, the maximum epochs and hidden layer and sparsity and alto regularizations. And it demonstrates a very low mean square error, which means the training is performed on a very optimal level at 53rd epoch, uh, which represents a very good quality of training done on the encoder with the least amount of error. So when the detection algorithm was run, So the islanding was initiated or simulated at 2 seconds, and the system was capable of detecting islanding within 20 milliseconds, um, or even lesser than 20 milliseconds. The maximum value recorded for islanding detection was maximum by 20 milliseconds, which is even more faster than the primary protection of the grid systems, bus systems, which is actually the overcurrent system of 100 milliseconds. So it's a benchmark in the islanding detection. Performance indicator. To indicate the performance of our indicated methodology, three analyses were done to demonstrate its significance: a power mismatch analysis, a statistical significant analysis, and harmonic analysis. The power mismatch analysis was done over different values of P and Q's mismatches, and detection time was calculated for over about 100 simulations, and was compared to under and over frequency protections with the proposed protection scheme, and which shows that the detection of time for proposed scheme is very low compared to the traditional. The secondary image shows the standard deviation in the proposed technique, which was noted to be 20.4 millisecond for the as a detection time with a standard deviation of 0.0029. Statistical significance was further evaluated for 1,134 cases with the root mean square value threshold saturated at 110 magnitude. And for all those cases, the statistical significant metrics, a confusion metric was established with which further concluded up to the F1 score of 0.991, precision of 0.982, recall of 1, security index of 99.5, and dependability index of 99.8, which is very highly accurate, precise, and dependable, and security wise a very stable system. Harmonic analysis was done in accordance with the IEEE standard 610032, which allows a plus minus 5% total harmonic distortion for a window of 20 milliseconds. And if we see on x-axis there are window size, and on the y-axis there is total harmonic distortion. And if you see the overlap of the two red curves is this corresponding region, overlapping region, and none of our reading measured reading lies in this indicated region, which ensures that our harmonic analysis technique is within the compliance with 610032 standard. So these were the results in order to verify the significance of our work at different initialization points at 1.25, 2.5, and 3.5 seconds, which was measured to be as an average on 4.56 total harmonic distortion, which was in compliance with the standard. A technical comparison was made with the existing literature. So hybrid methods, passive method, and followed by active methods were compared with our method in our paper, and superior you can say a superior characteristics were demonstrated here with the exceptional features of learnable pickups, an exceptional F1 score, and a good harmonic distortion with the least amount of time required for detection. So novelty and challenges in the work. So the novelty of our work is basically to produce a framework for intelligent detection system based on adaptive and learning settings. So they are not fixed setting or static settings. Neither they are dynamic settings. They are adaptive and learned settings. So they are continuously adapting to the system. The second point is the framework is capable of quantifying the statistical significance. Then a dialectic mode of validation, that is the online and offline validation, is presented. And finally, a computationally efficient, very efficient and fast responding with low power quality compromising framework is presented in the work. Challenges, as we know that in power systems, especially when it comes to control and protection, very limited data sets are available online. And even if they are presented, they are not, because very few times the fault is occurred between a very long duration. That's why data limitation is a problem here, and augmentation can be done in order to address the issue. Our decision for islanding detection is a black box right now, which is demonstrated by a deep learning on AI algorithm. So it's further aspects there to make our code more explainable to human understanding. Conclusion of the work. So this is the uh, summary of our result sheets, you can say. So there are statistical results which already presented in the last slide, then the inverter based parallel operation schemes and validation scheme dependability index. So it shows a superior algorithm than the traditional literature presented in the literature. Future works includes inverter universal protection for and control scheme designed for better grid penetration under weak conditions. So this is a new aspect which will be introduced in the coming future after a lot of inverter-based distributed generations are incorporated in the system. As discussed, using deep reinforcement learning, a way toward explainable intelligence control could be achieved in future of, of this research work. So our IEEE, our paper has already been under review in IEEE Access. Yeah, so that's it for the presentation. Uh, if there is any questions, I would be really appreciate.
Okay, yes, Sadiq, and good work, and you have presented very well. Your presentation was very well organized. Okay, you have particularly focused on some parameters related to frequency, pulse width, and one other was also among these. And finally, you concluded that you have achieved precision of 0.982. What does it exactly mean? 0.982, is it very high or comparable to the previous proposed works?
Yeah, that's a great question, ma'am. So the point of representing precision is that to ensure that every time when a detection is done, so how consistent our algorithm is. So maybe sometimes if algorithm is good, it can work on one condition very well, and on the same time the same condition appears, it might not work the same way. So precision is an indicator that for every time the situation appears, it works consistently. So 0.998 or 0.992 represents that means the system the algorithm is quite consistent over with high frequency. um, what was the later part of the question? Sorry, I just forgot that.
Okay, does this precision means we have achieved precision in all the three major parameters
Yes, exactly. For all
in
of the
your
three
case?
parameters, basically the whole scheme. This is the precision of the whole scheme, not for individual parameters. So the three of the parameters were combined together. Let me just demonstrate through control logic here. If you can see, all right. So this was the control scheme which was implemented, and all of the three parameters were incorporated in a single control logic. So now, despite they are
Okay,
three different parameters, but they are like acting as single parameter, and the precision, accuracy, F1 score, all are computed for the combined strategy, not for any individual parameters.
okay, good.